Study of electromagnetic radiation is very, very broad, but I'm going to try to summarize some of the key concepts in this short video. What we have realized in the last 200 years is that magnets have magnetic fields where there's an attraction from north to south. And hopefully, you've played with some magnets before and dropped some iron filings onto it. And you can see how the magnetic field will affect the pattern where the iron filings fall. Scientists have also studied electric fields. And there's a very, very similar pattern that you probably notice here between positive and negative components, such as, let's say, between a proton and an electron, or maybe it's between two atoms that have what's called dipoles. But you'll see that there's this electric field. And those that move on in physics, you'll study magnetic fields and electric fields. What we have also realized is that when we have certain types of radiation, or all types of radiation, is that the magnetic fields here in blue always operate at 90-degree angles or right angles to the electric fields, which are here in this kind of reddish pink orange color. And that they tend to move as waves, and they have a given wavelength. And you can see that there's this transferring of energy, and it's got a certain direction, and there's rules around which way the direction of the energy is. If we were to look at those waves a little more carefully, what we could see is that different waves, as we've learned before, have different wavelengths. So I've drawn three different waves here, and the top one, let's say the wavelength here is 5 centimeters. And I've got the exact same wave here with 6 centimeters, and the bottom one here is 4 centimeters. Just they're a little closer together. What we've learned is that the waves that have the smallest wavelength, where there's a greater frequency, where those waves are scrunched together, they have the most energy. And because of that high energy, they can get dangerous if it's very, very short wavelengths. And we also have ones with long wavelengths, and they would have less energy, and they're of less risk to us. Um, you know, we could have, like in this example up here, we have waves that are 5 or 6 or 4 centimeters apart. Well, what we've done is categorized these different waves based on their wavelengths. And, I said 4, 5, and 6, but it could be 4.1, 4.2, 4.3, or maybe it's 4.11, 4.12. We can have every little piece in between. So this is referred to as having a spectrum. Okay. And a spectrum basically means that we can have that 1 centimeter or two, but we can also have every number in between. So some objects will give off this radiation, some will give off this radiation, some will give off this. Some of them give off the radiation in between, and some of them give off all of those radiations. Anything that has that type of a wavelength, 4, 5, 6 centimeters, in fact, from about 1 centimeter up to 10,000 centimeters, they have categorized these, and we refer to them as radio waves. And you've experienced radio waves before. What if they were smaller? What if they were shorter wavelengths, higher energy, higher frequency? Let's say from 0.0001 centimeters up to 0.05 centimeters. Well, these would be what we call infrared wavelengths. So there's a whole broad spectrum, a whole broad range of waves that get categorized as a group. It's not one individual wave. You don't just say, hey, 3 centimeter of wavelength is radio and 4 is something else. There's a whole group of them together. This diagram helps us see that a little bit. So you can see here, I've got an example of a wavelength that's really, really long, and these are my radio waves. Here's some in here. Let's go to a different color. Here's some here. This one here, a little shorter. This is my infrared wavelengths. What if we go in here from, say, here to here? Wow, even on the diagram, it's not easy to see, but you get into here, it's known as ultraviolet. And I'm going to talk more about the names in a minute. What if I have, let's say, from here to here, this wavelength? You see that these wavelengths are getting shorter and shorter as I go along. And this blue one here, these are a group of wavelengths that they call them X-rays. And then once again, we got shorter again, way up here. These are really short ones here. These are my gamma rays. Once again, as we get up into this end of the spectrum on the left of this diagram, we see that the wavelengths are really short, so the frequency is really high. But once again, what we need to realize is that our energy increases as we get over to this side. And the energy can be dangerous. There's a little tiny, tiny range here, right in the middle, right here, that little tiny bit. And what we've done is we've made it a little bit bigger down below because these are very special wavelengths. In here, in around 380 nanometers, to the other end of this, down here at around 740 nanometers, and different diagrams, different websites, different textbooks, whatever, will give slightly different ranges. But these are the colors that our eye can detect. Okay, so let's just think about that for a second. Here's my eyeball. Little eyelashes going off here, right? And I got a little hole in the end of my eyeball. And what happens is that these waves are coming in, and some waves don't get into the eyeball. Other waves are the right wavelength and they go through, and then they hit to the nerves at the back of our eye. Back of our eye, we get some nerve centers back here that can pick up these waves, and our rods and our cones and so on. That's where it gets picked up. But if it's not the right wavelength, it's not going to get picked up in the nerve centers, and then it goes off to the brain. It doesn't get picked up there. So we have to have the right wavelengths so that our brain can see it. And this has happened over time, that our body has evolved to handle those wavelengths. I do want to mention that some diagrams have the gamma rays on the left and the radio waves on the right, and some others have it back the other way. Neither is correct or incorrect. Just be careful which one you have. I have another one here that shows the different visible lights, and you'll notice that this one is backwards. This one has the red on the left, where the other one had the red on the right. So just be very careful. Once again, you'll see that this one has it in around 780. The previous diagram had it in around 740. Okay. But you'll notice that there's an end of the spectrum that is red, and there's an end of the spectrum that is violet. And one of the key things to remember is that at the violet end of the spectrum, once we get past what we can see, once we get past that wavelength that our eye can see, we go from violet to ultraviolet. And ultraviolet is fairly high intense energy, and it does cause a little bit of damage to us. And that's where our sunlight, our UVA, UVB, so on, sunlight that's going to cause damage to our skin. That's why tanning is dangerous, and especially those tanning beds. It's this ultraviolet radiation here is quite dangerous to us. On the other end of the spectrum here, we got red. And if you go past the end of red, you're going to hit infrared. So that's how I remember which one's dangerous and not so dangerous. For me, I know that ultraviolet light is super dangerous all my lifeguarding days, avoiding UV light because I don't want skin cancer, trying to avoid it because this ultraviolet radiation is so bad. So the violet is higher energy and dangerous, whereas the red is lower energy, not as dangerous. And we use infrared for a lot of things. Okay, so just be cautious, but here's some wavelengths as given by the spectrum. Now, as we start doing, you're going to notice that I got some prefixes here, NMs. And what does that mean? So these are once again our SI units, our System International, commonly called our metric prefixes. And we've got some numbers here that are pretty big. And you've heard some of these, especially in our phones and computers. You've heard about terabytes or gigabytes or megabytes or even kilobytes. Okay, so kilo 10 to the 3, mega 10 to the 6, giga 10 to the 9, tera 10 to the 12. On the other end of the, once again, a spectrum, the other end of the spectrum, things that are really small, like milliliters or milligrams. Here we have micro, things that are micro. And when you talk about micrometers, you might also hear the word microns. Okay, that is micro. Oops, the symbol. I better put it proper symbol because I put in microns, because this is a small m millimeter. This is a big M megameter, but micrometer is, wow, we've seen that symbol before. If you want to go back to our unit on friction, that'll, it's just a symbol. And that's the symbol that we use for micrometers. Okay, and then we got nanometers, nm. Okay, so when we looked at visible light, we saw that it might have been, say, 500 nanometers. So, what did some of these numbers mean? So, an example, if I told you something had 3 times 10 to the 12th, so 3 times 10 to the 12th, that's 3 tera, whatever. So, 3 times 10 to the 12th would be 3 with 12 zeros after it. Or my decimal that was here moved 12 places. Likewise, if I had something 10 to the negative 9, 10 to the negative 9, that's nanos. So if I had 4 times 10 to the 9, it would be like if I put my decimal there and then moved it 9 places to the left. Okay, so this is a really small number. This is a really big number. And that's why we use this scientific notation. So very quickly, we do a sample question. What is the wavelength if we have 2.6 gigahertz? Okay, well, we know that the speed of light is equal to the wavelength times the frequency. And what scientists have discovered over time is that this electromagnetic radiation is the same speed as light. Because light, the visible light, going back to here, all of the stuff, the gamma rays, the X-rays, ultraviolet light, the visible light, infrared, radio waves, all these waves all move at the speed of light. So that's kind of cool. So if I want to know, let's see, what is the wavelength? So a little bit of algebra here. I'm going to just say, okay, so my wavelength is equal to C divided by my frequency. Well, we know that C is the speed of light, so that's 3.00 times 10 to the 8 meters per second, divided by my frequency. Frequency in this one is 2.6 gigahertz. Gigahertz doesn't mean seconds. So I need to do something with that. Now, you can convert it into seconds, but here's what I'm going to do is I know that a gigahertz, go back to the other page here, giga is 10 to the 9. So all I'm going to do is I'm just going to make it nice easy. I'm going to go 2.6 times 10 to the 9. And remember, hertz is per second. Or I could have written that as seconds. Oops, not to the 9. I could have written that as seconds to the negative 1. And when we do our unit analysis, we'll see that the seconds here and the seconds there cancel out, and we're left with meters, which is a good unit for our wavelength. So let's see. So I've got 3 10 to the 8 divided by 2.6 10 to the 9. Pop that into my calculator. I'm going to get 0.1153 meters, or maybe I could write that as 11.53 centimeters. Okay, so where does 11.53 centimeters fall on my diagram? So 11.53 centimeters. It's going to be sort of like around here. Guess what? Those are radio waves that we just looked at. Okay, so those are radio waves. And we didn't know that from the problem, but we can use our table and go look that up. Okay. So, so for instance, a radio station here in the city might operate at 2.6 gigahertz, and the radio in my car is programmed to handle and receive waves of that wavelength. Okay. Let's do another one. The most common light that we can see, the most visible light is, let's say, 550 nanometers. That's our most visible light. What does that mean? Well, let's see. Once again, I'm going to write this out as 550, and nano. Go back to my table here. Nano is 10 to the negative 9. So I'm going to go 10 to the negative 9 meters. I could have written that as 550 nanos, but same thing. Now, I do want to mention that this is not scientific notation. This is improper scientific notation, but my calculator understands it, so I can pop that number into my calculator. Once again, if I want to calculate what is the frequency of this light, and okay, 550 nanometers. 550 nanometers is sort of somewhere in around here. It's a bit of a yellow green light of some sort. Okay, so we got this yellow green light, and once again, C is the wavelength times the frequency. So if I want to know the frequency would be C divided by the wavelength. So the frequency of this would be C, once again, speed of light, 3.00 times 10 to the 8th meters, divided by the wavelength. Now, which one's easier to use? I'm going to use this one here because it's in meters. So 550 times 10 to the negative 9 meters. Okay? 550 times 10 to the negative 9 meters. Well, that's going to give me a frequency of, let's turn that on. Okay, so let's see, we got 3e to the 8 divided by 550 e to the negative 9. Oh, that's going to be a huge number. Let's take a look. I'm getting the frequency here is 5.454545, oh, repeating decimal, times 10 to the 14th. Oops, that was meters per second there. Hertz. Now, maybe the problem asked us to convert that into, I don't know, gigahertz. So that would be, 54545 gigahertz, because giga is to the power of 9. Gigahertz is 10 to the 9. So I just took away 9 from that, and so I had 5 left. Let's see if I got enough places here. 1, 2, 3, 4, 5. Oh, not quite. You should have another 4 there. Okay, let me just tidy that up. I got to have these spaced properly if you're going to write things in proper scientific notation or proper notation. So it's 545,454. All right, there we go. Gigahertz. Now, lastly, let's just talk about where does this radiation come from? Okay, now, first of all, we need to realize that everything is giving off radiation. Okay, today was a nice, beautiful, sunny day, and I got some radiation. I got some sun hit me today, and I'm kind of warm right now. So during the day, I heated up. Well, on top of that, I've also had food to drink, food to eat, water to drink, and my body is going through some chemical reactions right now as I burn off this energy to create, or burn off the calories to create energy to keep me awake and make this video. So I'm absorbing energy all day, but at the same time, what's happening now is I am also, upside down person, I'm now giving off radiation. Okay. And we're all giving off radiation at all times. I'm giving off infrared radiation. and that is electromagnetic radiation. Now, it's low energy, it's not going to hurt you, but, it's kind of neat to say that, we've all got some kind of vibe about us. Well, it's true, we do. We are all vibrating. We're all giving off this electromagnetic radiation, and it all has wavelengths, and it all has some kind of frequency and wavelength. There's energy about us. And I think some people have more energy than others. But also things like our sun. Our sun is giving off a lot of radiation. And what it does is it gives off all kinds of radiation. It gives off everything from our gamma rays, it gives off our X rays, it's giving off our infrared, it's giving off the visible stuff that we can see. It's giving, UV, I put them in the wrong spot. Let me fix that. UV should be here and IR there. Ultraviolet, that's the dangerous one. And then we've got our infrared, we've got our radio waves. So our sun is giving off all different types of wavelengths. And then that's what makes it so important to life on Earth. Let's do another question. What if we were asked to compare the frequencies of violet and red? And I'm not saying how often do you see these colors. I'm asking, let's compare the frequency, the implications of the wavelengths. So first of all, if I was to look at violet, I'll use my blue here for now. Violet is 380 nanometers as my wavelength. And red, if I remember correctly from a previous diagram, red was in around 740 nanometers. Don't forget our key equation that the speed is the wavelength times the frequency, and we know that this is the speed of light, which is the key piece to this whole thing. Okay, so to calculate our violet, once again, I'll just do the formula. I'm going to do the algebra once here. Frequency is C divided by wavelength. By doing that once, I can make it easier on myself. So I'll see the frequency of the violet will be equal to 3.00 times 10 to the 8th meters per second divided by 380 nanometers, which is 380 times 10 to the negative 9 meters. Once again, not proper scientific notation, but that's okay. And we're going to get the frequency here of this. This is going to be 7.89 times 10 to the 14th hertz. I'm just going to round that off here. That's somewhere around 8 times 10 to the 14th. Okay. If I do the exact same thing for red, I'm going to get the frequency of my red here is going to be 3.0 times 10 to the 8th meters per second. Divide that by the wavelength, which was in around 740 nanometers. Actually, replace that nanometers with 10 to the minus 9 meters. And I'm going to see that the frequency of red light is somewhere in around 4.05 times 10 to the 14th hertz. And I'm going to round that one off just so for argument's point of view here is that that's in around 4 times 10 to the 14th hertz. Okay. What I would like you to recognize is that if you compare these two numbers, this one is 2 times the size of that one. Okay. The frequency of my violet, okay, has twice the frequency of red. So in other words, here we're going to see 8 times 10 to the 14th waves every second. And this one we're only going to see 4 times 10 to the 14th waves every second. This one we're going to see way more waves, double the waves over here that we see on that one. And it's the number of waves that's creating that energy.